Good morning to all. My name is Sanamdeep Singh. Today we will be discussing the brief operation of induction generator. So let us start. Today we will discuss three parts of the induction generator. First one is its general working and its principle of operation, and the third thing is self-excited induction generator. So we will be having focus on these three topics. So first of all, let us start with the general operation of induction generator. So in order to understand the induction generator, we have to first analyze how induction motor works. So let us say you have a three-phase induction motor which is having a stator and a rotor. If we give a three-phase supply to the stator of three-phase induction motor, we know that whenever a three-phase supply is provided to three-phase winding of the stator of induction motor, which is spatially apart by 120 degree. The electrical signals are also 120 degree apart electrically. Now what will happen due to the winding arrangement in the stator, the three-phase winding, we will get a rotating magnetic field. We will get a rotating magnetic field which is known as RMF, rotational magnetic field. This will force or this will develop a torque in the rotor itself. Now let us say the RMF is moving in this direction clockwise ns, and the speed of RMF is generally given by the notation ns. It will develop a torque within the windings of the rotor, which are either squirrel cage windings, which is a squirrel cage itself, or it can be a specially wound rotor windings. What will happen? The torque will develop in this direction and the rotor will start moving in the direction of rotating magnetic field. So in this way, induction motor works. But what is the case? Here we have ns greater than nr, means the speed of rotational magnetic field is always greater than the speed of rotation of the rotor, which implies that there will always be a difference between ns and nr, and this is known as slip. In this case, the induction motor, the rotor always follows the speed of the induced magnetic field, which is the rotational magnetic field. Now, further, if we increase the speed of nr, let us say if we increase the speed of nr, what will happen? A stage will come when nr will become is equal to ns. What will happen then? Then the slip, the value of slip will become 0. Then what will happen? The induction motor then work as a no load motor. That means it will neither draw any power from the grid, neither it will supply any power to the grid. It is acting as a zero load on the three-phase grid. I hope this operation will be clear. Now, in the second case, let us say we have increased by somehow method, by using any external machinery, we have increased nr greater than ns, means we have made forcefully the rotational speed of the rotor greater than the synchronous speed, that is the speed of the RMF generated by the three-phase supply or three-phase electrical signals. What will happen then? So the slip will become negative because the formula of slip is ns minus nr, and in this case, with this formula slip will become negative. It will become less than 0. Now what will happen? The torque which is dependent on slip, it will become also negative. What it will do is it will reverse the direction of the current induced in the rotor windings. Then what will happen? In this case, the field generated in the rotor will now develop in opposite direction to that of induction motor. It will be in opposite direction. So in a way, it will oppose the rotational magnetic field that is being produced in the stator windings. This will result in production of current. Rather than drawing current from the grid, it will supply some current to the grid. So this is the operation of induction generator. So what I am trying to say is, whenever NR is made greater than NS, torque generated in the rotor becomes negative, and current is also generated in reverse direction. This generates a magnetic field that opposes generates a magnetic field in the rotor that opposes, it always opposes the rotational magnetic field produced in the stator, which produces a active power, and it, instead of drawing power from the grid, it supplies power to the grid. So I hope you would have understood this. So what is the next case? In this particular phenomena, let us say we are having an induction generator. This is the rotor, this is the stator, and if we move rotor greater than the speed of stator RMF with the help of a prime mover. So this is the prime mover. Prime mover is any engine, is any kind of device that forcefully increases the speed of the rotor, and it increases beyond the synchronous speed. So instead of drawing power from the grid, it supplies active power. So it draws reactive power and it supplies active power when NR is made greater than NS. So this is the basic operation of working principle of induction generator, and the part 1 is finished. You can take the screenshot of the diagram. Okay, so this was the diagram of induction generator, in which there is a prime mover which is used to increase the speed of rotor beyond the synchronous speed. This develops a negative slip, which in turn develops a negative torque in the rotor windings, and this induces a current of reverse polarity which is supplied back to the grid. So the current which is supplied back to the grid develops active power. The current which is drawn from the grid, which is used to produce rotational magnetic field, it draws reactive power. So induction generator draws reactive power from the grid and supplies active power to the grid. In this way, it acts as a induction generator. So one thing is mandatory, it always requires some kind of excitation for the windings of the stator. So it can be through the grid itself, to which it will supply the power, or it can be done with the help of external capacitive bank that we will study in the self-excited induction generator. Okay, now let us continue further to understand the principle of operation of induction generator. So in order to understand the principle of induction generator, we have to consider two cases. First one for the motoring mode and second one for the generating mode. So case 1 is for motoring mode. Let us consider case 1, how induction motor rotates. We already know there are total 3 set of windings in the stator itself, and there are set of shorted windings in the rotor core. So I am considering here only 2 windings in the stator in order to understand only the operation and how torque and current works in the induction generator and induction motor. So let us start. Consider this is a rotor. And these are the windings of the rotor itself. So the yellow one is stator and the white one is rotor. So there are windings. So there are windings in the rotor. Let us consider these windings are A and A dash. Now let us suppose we have supplied a three-phase supply to the stator of induction motor. We already know a three-phase RMF will be developed. Let us consider at a particular instant, on this point there is north pole and at this point there is a south pole which is being developed. Let us say the rotation of this field is clockwise, which is given by the notation ns. Now, to understand the operation, we have to consider Faraday's law. So whenever a conductor, so these are the hollow conductors and these are the hollow spaces in which conductors are placed, and this is the front view of the motor. And as it will be in this kind of direction and there will be a huge motor components behind this. So these, you can assume that these windings are inside the board, these are inside the board, these are inserted inside the board. Now what will happen? Whenever a conductor is placed in changing magnetic field, there is always an induced EMF and induced current in itself. Now consider this is the direction of rotational magnetic field. Let us say it is linearly moving in this direction. NS is moving in this direction. Now at the starting, this thing is stationary, rotor is stationary. What will happen? If let us say there is a person standing on the rotor itself, for assumption, if something is moving in this direction, from this to this direction, this person will observe that I am moving in this direction. So if field moves in this direction, the motion of the rotor, apparent motion, not the actual motion, but the apparent motion of the rotor will be in this direction. Now we can use Faraday's right hand rule. In order to find the direction of the current induced in the windings of the rotor. Now let us say this is your right hand, this is the, and in the Faraday's law, not Faraday's, it was my mistake, it is Fleming's right hand rule. We use Fleming's right hand and Fleming's left hand rule in order to find the direction of the motion and in order to find the direction of the current. Here we will use Fleming's right hand rule in order to find the direction of the current induced. What will happen? So the thumb gives you the direction of the motion, the first finger gives you the direction of the field, and the third finger, which is the middle finger, it will be pointed towards the direction of the current induced. Now this is the field from north to south. So field is in the north to south direction and the rotation of the rotor is in the right direction. So your finger will point outwards. So the current here will be outwards and we represent the outward flowing current with the help of a dot in the conductor. So dot means outward current and cross means inward current. Now consider this winding A dash. These are interconnected behind the from the back side. So consider this. You will get that by using Fleming's right hand rule, there will be a cross. That means the current will be flowing inward. Now for the stationary rotor, we have found the direction of the current. Now what will happen? We know that whenever a current carrying conductor is placed in a changing magnetic field, it has always been exerted by some kind of force that will give us the direction of rotation of the rotor. Now take Fleming's left hand rule. Force, field and current. Now we are having the direction of the current. We are having the direction of the field from north to south, and what is the direction of force which is being exerted on the rotor itself? It will be in this direction. So the torque acting upon this particular point will be in this direction. Similarly, the torque acting on this point will be in this direction. Now its axial is fixed. It is on a shaft. The rotor will rotate in clockwise direction, which is the same direction as that of NS. So NR will always follow NS. This is the case first for the principle of induction motor. I hope this will be clear. You can take the screenshot of this. Now let us have a look on case 2. This was the case first for the principle of rotation of induction motor. Now we will consider the principle of induction generator. So in the case 2, we will be studying how rotation and torque changes in induction generator. What will happen? Consider again, this is the rotor. This is the rotor itself. And this is the stator. Again, the outer part is the stator and the inner part is the rotor. So this is the rotor itself. Let us say, again there are two, we are considering only two windings instead of considering all the three windings, just only to understand how force and torque acts in case of induction generator. So this is winding A and this is A dash. Now, let us say again, here is the north pole and here is the south pole, and the RMF is rotating in this direction. RMF is rotating in this direction clockwise, and the rotation is NS. Now we know in induction generator we have applied a prime mover which can increase the speed of rotor beyond the synchronous speed. Now we again need to find the current in the windings of A and A dash. We know the direction of now NR is this, which is clockwise or which is in towards the right side direction. Again we use Fleming's right hand rule in order to find the induced current. So use Fleming's right hand rule. There is a rotation in this side, and movement of the direction of the field is from north to south, direction in this side. The current will be inwards. Now the current will be inwards. You can do it too to understand this concept. So if the current is inward, we use cross sign. Similarly, here in the A dash winding, the current will be outwards and there will be a dot. Now we have achieved a point where we have found the direction of the current. Now there is a current, there is a rotational magnetic field, and there is a rotation of the prime mover. We have to find the direction of the force acting on the rotor from the machine itself, not from the prime mover but from the machine. Now we use Fleming's left hand rule. We will use, so in the case 2, let us again start with the case 2 itself. So in the case 2, we are moving rotor beyond the speed of RMF with the help of a prime mover. So we have to find the direction of the current in the windings of the rotor. Now the rotor is rotating in this direction, and there is a field which is in this direction from north to south. So we can use Fleming's right hand rule. We can use Fleming's right hand rule to find the direction of the current in the windings A and A dash. Now consider your right hand. This is the rotation of the you can say direction of the force which is being supplied on the rotor with the help of prime mover, and this is the field direction of the field, and the current will be inward. So I have put a cross over there. This will be the direction. Force, field, current. It will be inward. The current will be inward. Similarly, the current will be outward in the winding A dash. Now we have found with the Fleming's right hand rule the direction of current. Now we have to find direction of torque acting on the rotor windings by using Fleming's left hand rule. What will happen? with the Fleming's left hand rule, what will happen? The current is inward. The current is inward. And the direction of field is downward. The torque acting will be in the opposite direction. So this is the direction of torque. Consider the case 1, the torque was in this direction. In the case 2, the torque is in this direction. What will happen? This means torque is negative. Current produced will be opposite to that of the current in the case 1, and there will be a reverse magnetic field and reverse current will be generated in the windings of the stator. That means whenever torque becomes negative, the induction machine provides, instead of drawing power, it provides active power to the grid. It provides active power to the grid itself. So the second point is finished. Okay, so now you can take the screenshot of this. We will continue to part 3. In the part 3, we have to consider self-excited induction generator. What we do is, as we have studied, we always need some kind of reactive power for the grid, from the grid, so that stator can make RMF. Now, we mostly use induction generator in the remote places. So how RMF will be generated without the grid, where electric supply is already not available? That's why we need any kind of generator. So we use a set of power banks, a set of capacitive power banks. Different capacitors are used, to which a little supply is provided, and they provide increased current to generate the RMF. Let us understand how this happens. So consider there is a prime mover which is supplying rotational force to the rotor itself, and it is giving supply to any kind of load. But if there is no grid itself, what will happen? We will connect a capacitor. We will connect a capacitor bank. So in this way, a capacitive bank is attached to the induction generator so that it can itself generate the rotational magnetic field. How this happens? So this is the graph of magnetizing current and voltage which is being present due to the residual magnetic field or development of voltage in the stator itself. So this is the graph for between the voltage and magnetizing current. This voltage, it is the residual voltage which is being present in the windings of the stator itself. What will happen? If we connect the capacitor, the graph of capacitor is like this. This is voltage and this is current. On the y-axis there is a voltage, on the x-axis there is a current. The graph will be like this. If the value of capacitance is high, the graph will be like this. If the value of capacitance is low, the graph will be like this. So C1 greater than C2 greater than C3. Now, if we connect this stator to the power bank, what will happen? Due to residual magnetic field, there will be some supplied current to the capacitors. So capacitor only supplies current when there is an input. So whenever there is a little input to the capacitor bank, it supplies a huge current. So whenever there is a little voltage, it goes to the capacitor and then capacitor supplies current corresponding to its own value. Again, voltage is added up into the stator windings. This again supplies a little current to the capacitor. Capacitor again supplies a little voltage to the stator itself, and in this way voltage is added up. In this way voltage is added up until a point when it achieves its saturation or maximum value. After that, the capacitor on its full efficiency gives the maximum current or voltage to the stator windings, which is needed to develop the rotational magnetic field. So with the help of capacitor bank, rotational magnetic field can be itself generated in the induction generator. I hope you would understand this lecture better, and in case of any doubts, you can mention the doubt